Okay, Andrea, can you start? Ah, it's already recording. Sorry. Okay, so I'm gonna start. Hello, everyone, and welcome again. So it's a pleasure to invite to have Kyle Pratt here from University of Oxford, and he'll speak on Landau-Siegel zeros and central values of L functions.
Great. Thank you very much for the invitation. I'm going to have my video off just for bandwidth reasons. But, if you have any questions or anything, feel free to just, shout something out. Okay, so I'm going to be talking about Landau-Siegel zeros and central values of L functions. I should have put it on this slide, but forgot to, that I'll be talking about some joint work with my collaborators, Bui and Alexandru Zaharescu. So just so they get the proper credit. So as I said in the abstract, I'll be doing a little bit of a historical survey, a gentle introduction, maybe for those people who don't think about this sort of thing very often. And then gradually we'll get a little more technical, and maybe by the end, there will be some treats for the experts. But that's the general outline that we're going for. Okay, so Landau-Siegel zeros and class numbers. Okay, so we know that Dirichlet basically invented analytic number theory in his famous proof that there are, primes in any given primitive residue class. And he invented these Dirichlet characters, and the non-vanishing of this L function, L1 at 1, was sort of the main part of the proof. Okay. So showing the L1 chi is non-zero is the important thing. And analytically, showing that something's non-zero and showing that it's not too small are more or less interchangeable. Okay, so if chi is complex, this is pretty easy because you have two characters to work with. If L1 chi is small, then also L1 chi bar would be small. But then you have these real characters, and they're a different beast. They make things a little more tricky. So this is why Dirichlet developed his class number formula, so he could show this non-vanishing here. So we have this nice expression for L1 chi d in terms of the class number of this imaginary quadratic field. Okay, so this relates these two different nice, interesting things. And the class number is just the order of a finite group. So it's a positive integer, and this gives you some sort of lower bound on L1 chi d. And the constant is effective. Okay, so sometimes you really care about the constants and you maybe want to do some numerical work, and effective constants are important. Okay, so this is basically how Dirichlet proved his theorem by using this class number formula. And it gets this nice lower bound. We'll talk about more later. So just for notation, whenever we write chi, it's always going to be this primitive real Dirichlet character mod d. Okay, and this will be showing up a lot for us. So you have this lower bound. It's effective, but usually it's not strong enough. I mean, you're basically just putting in some trivial information that the class number is at least 1. Okay, so there's no real arithmetic content there. So you would want something much stronger. The best possible bounds up to constant factors come from the generalized Riemann hypothesis, GRH. This gives you something on the order of log d for an upper bound and 1 over log d for a lower bound. Okay, so these are of course much better. The lower bound is of course much better than 1 over the square root of d. And unconditionally, you can get sort of a reasonable upper bound of log d, but the lower bounds are, of course, more difficult and usually more important. And from our modern vantage point, we know that the reason these lower bounds are difficult is because there could be a real zero of this L function, and this real zero could be very close to 1. Such a real zero will be a Landau-Siegel zero, or sometimes just called a Siegel zero. So we'll denote it by beta when it comes up. So you have the classical zero-free region, and this is where you read it in Davenport or something, that we know that there is at most one real zero in this region. And we would say that chi is exceptional, or that it has a Landau-Siegel zero, something like this, if this real zero does exist. So beta in particular is larger than 1 minus 1 over log q, something like this. So we would love to show that these things don't exist. If they do exist, there's sort of the strongest possible counterexample to the generalized Riemann hypothesis. So naturally, we're very interested in ruling out the existence of these things. And it's a classical result of Landau that even if they do exist, they don't show up very often. Okay, so sometimes you can use the fact that even if they don't exist, they only show up rarely, and that can be enough. So some other classical results, Hecke showed that if there is no real zero in this zero-free region, then you do have a nice lower bound. You get a 1 over log d, which is very nice, matches sort of symmetrically with the upper bound of log d. And if you had this lower bound, then you get a very respectable lower bound for the class number, okay, the square root of d over log d. And this is, essentially what we expect the class number to be. It should be about size the square root of d. So this is if there is no real zero. And then if you do some contrapositive, logical maneuvers, well, that tells you that if L1 chi is smaller than this, then there should be some sort of zero nearby. And we're really interested in exploring the consequences of the existence of a Landau-Siegel zero. If one of these zeros does exist, what sort of things happen? Okay, so we have this lower bound on L1 chi, this effective lower bound coming from Dirichlet's class number formula. There are stronger lower bounds, but they're ineffective. These implied constants, there's no way that you can actually compute them. So Landau had the first result in 1935. He got 1 over d to the 3/8, and Siegel just sort of did his argument, but better, basically, and got our, the now classical 1 over d to the epsilon. And this is still the state of the art. So you have this nice lower bound, the class number larger than d to some small positive power. So we know that the class number grows somewhat quickly. But if you were actually interested in, solving the Gauss class number 1 problem or something, you can't use these ineffective results to do it. So theoretically, these are nice results. But if you cared about actually explicitly writing some things down, explicitly calculating, this isn't helpful. The strongest effective lower bound comes from some very, impressive technical work, Goldfeld, Gross, and Zagier, using elliptic curves and some other nice things. And this lower bound on the class number is only logarithmic in d, essentially. You can still do some nice tricks and use this to solve the class number problem for fixed h that are small. So Watkins, for instance, has done this for all the h's up to 100. That was back in 2004. And it'd probably be a nice problem for someone to, try and go a little bit higher than 100, see what they can do. And some of the ideas behind this Goldfeld, Gross, Zagier work will come up again later when we start getting into a little bit of the technical details of things. Okay, so that's just by way of very general overview. And you might ask, okay, well, what does that mean for proving theorems? How does this work in the mathematical daily life? And it's really interesting that we usually think about Siegel zeros as being some sort of curse, some sort of very bad thing. And that if they show up, this sort of ruins your life and it makes it so you can't prove the theorem you want to prove. But we're going to see that also there are some very nice things that you can do if these zeros do exist. So take Linux theorem on primes and arithmetic progressions as a good example. So here's the statement of Linux theorem. There's some absolute constant, capital L, so that in any primitive residue class A mod D, you can find some prime less than D to the L. Okay, so think here L being 5, like this is the current record due to Xilores, or 10 or 20 or something. And this is actually some pretty advanced analytic number theory. Some really nice ideas go into this proof. And it's rather non-trivial because the usual Siegel-Wallfisch theorem would give you something essentially exponential in the modulus. So Linux theorem is quite a substantial improvement. Okay, so how does this theorem actually go, at least in the classical formulation? Well, at first glance, it seems like maybe if you have one of these Landau-Siegel zeros, then it's much harder for you. Okay, so recall from Davenport, you have some sort of explicit formula thing. So if you're looking at primes in this residue class A mod D, you have some sort of main term, chi over phi of D, and then you have this secondary term involving the Landau-Siegel zero. Okay, and then there's some sort of error term involving some other zeros. So this is what the main term would look like. And of course, we don't think that this Siegel zero should exist. So we have this sort of weird factor messing with the main term, and we want to know how badly things can affect it. Okay, well, beta is close to 1. So actually, we see that things could get really messed up. If chi of A is -1, okay, so if A is, think, A is like a quadratic non-residue or something, well, then the main term is actually about twice as large as we expect it to be. We think the prime should somehow be equidistributed in residue classes from randomness heuristics or something. But actually, if you have the Siegel zero, then some of the residue classes get twice as many primes as they should, twice as much as their fair share. And then you see that if chi of A is 1, then that thing in parentheses almost cancels out. And you actually have to work relatively hard to show that you still get some sort of positive contribution here. Okay, so it seems like finding primes in at least some of the residue classes should be problematic, should be difficult. And this is the distorting influence of this Landau-Siegel zero. Okay, so the zero being so close to 1, it has a very strong distorting influence. And you see that exactly from this explicit formula here that we've written down. Okay, so that all sounds really bad. That doesn't sound very helpful, very nice. But actually, you can get much better values of Linux constant when this zero actually does exist. Okay, so I said that this error term from Davenport's explicit formula that involves a sum over zeros over ls psi, so these are other Dirichlet L functions, with size being characters modulo d. And there's this very nice phenomenon called the Düring-Heilbronn phenomenon, that a Landau-Siegel zero, if it exists, it pushes all other zeros of all other L functions farther away from the 1 line. So on the one hand, you're losing because you have this nasty zero close to 1, but on the other hand, you're actually winning something. The zero is pushing all other zeros away. And it turns out that by playing this game, you can actually prove Linux theorem. And you can go even farther. So you could assume some stronger properties of your Siegel zero. Assume that it's, L1 chi is very small, essentially. And Friedlander and Ivanitz have thought a lot about this. We'll see their names come up again several times. And they show that if you actually have a very strong Siegel zero, or a Siegel zero that's very near to 1, then you can actually show that Linux constant is strictly less than 2. Okay, so 2 minus 1 over 59, something like this. And that's actually rather remarkable because even the generalized Riemann hypothesis only shows that L is less than 2 plus epsilon. So assuming the generalized Riemann hypothesis, we don't know how to go below 2. But if you have a strong Landau-Siegel zero, you actually can go strictly below 2. So in some sense, a Landau-Siegel zero is giving you something even better than GRH. Okay, so you might think that this is just some sort of like weird one-off, that, okay, I'm looking at primes and arithmetic progressions. There are some zeros involved. Okay, this Landau-Siegel zero doing weird zero things. But this is actually not an isolated phenomenon. And there's actually lots of really interesting things that happen if Landau-Siegel zeros do exist. Okay, so something you could do is you could assume that these Siegel zeros exist, and then you could try and prove something about it. Friedlander and Ivanitz like to call these results illusory, because of course we don't actually think that these Siegel zeros exist. We all, we all being faithful number theorists, we all believe in the generalized Riemann hypothesis. So such things, of course, don't exist. But I think there is some value in proving these illusory results. Okay, so one potential justification, I suppose, is that many results in number theory, like Linux theorem, require some sort of bifurcation. You have a case where this zero exists, where this bad zero exists, and you have some argument for that. And then you have some other case where it doesn't exist, and you need some other argument for that. Okay, so this sort of thing shows up. So there are cases where you just genuinely have to deal with, what if this zero exists? And maybe more philosophically, you might think that these illusory results, they're probing the strength of a Landau-Siegel zero. You're seeing, what sort of consequences flow from the hypothesis that Landau-Siegel zeros exist. And this should give you some sense, maybe, of where this, where these Landau-Siegel zeros sit in the pantheon of number theory. So this gives us a way to measure the strength of our tools, our intuition, the power of our technology, and see how close we are, for example, to actually showing these things don't exist, right? And I think you can make a good case that we're not very close, that we have maybe a long way to go. But as you study these sorts of things, as you look at these sorts of results, it does give you a sort of feeling about what's going on and what you would actually need to show that these things don't exist. Okay, so let's talk about some illusory results. Some of these we've already discussed. So, okay, so it's classical that if you have a Siegel zero, then the class number h of minus d is smaller than you expect. Okay, so this is sort of what we talked about. Similarly, half the arithmetic progressions contain twice as many primes as expected. Okay, so this is sort of a weird thing that you wouldn't expect to have happen. On the other hand, there are things that you do expect to happen. So for instance, if there are Landau-Siegel zeros in some specific descents that I won't get into here, then you can actually find infinitely many pairs of primes p and p plus h, for any fixed even h. So if there are Landau-Siegel zeros, you can actually show that there are twin primes. Okay, so we don't know how to do this unconditionally. This is a very hard problem. But if you put yourself in this illusory alternative world where Landau-Siegel zeros exist, then somehow this hypothesis is a very strong piece of information, and you can prove theorems that are completely out of reach of what we know how to do. Okay, so Heath-Brown showed you can get twin primes and other prime constellations. And I think Heath-Brown's result here in 1983 was sort of the modern genesis of this, this vein of ideas of these illusory results. And then Friedlander and Ivanitz and some others have really taken the baton and done some cool things. Okay, so you can see here another consequence is the existence of primes in short intervals. So this is a very classical problem in analytic number theory. If I have this interval x minus y to x, and I'm thinking of y as somehow being small compared to x, are there still primes in this interval? And if there are Landau-Siegel zeros, you can actually take y to be slightly less than the square root of x. And again, this is something really amazing because even the Riemann hypothesis only lets you get down to a little bit more than the square root of x. So again, this is another situation where the Landau-Siegel zeros are somehow penetrating deeper than even the Riemann hypothesis or its generalizations can go. You can find primes of very interesting forms. So you could look at primes of the form a to the 6th plus b squared. This is a very thin sequence. The number of primes up to x would only be about x to the 2/3. We don't know how to show that these exist unconditionally. And if you can handle a to the 6th plus b squared, well, you should also basically be able to handle this other polynomial. This is a discriminant polynomial. And Friedlander and Ivanets study this, again, under the assumption that these Landau-Siegel zeros exist. And if you get prime values of this discriminant polynomial, what this turns into is the existence of infinitely many elliptic curves with only one place of bad reduction. Okay, so this is kind of a very cool special thing. Of course, we think we should be able to prove a lot of these theorems unconditionally, but we just have no clue how to do any of that. All right, just a couple more of these illusory results. It's an old conjecture of Hardy and Littlewood from the early 1920s that every large non-square integer is the sum of a prime and a square. So every large capital N, I should be able to write as n equals p plus x squared. And if chi mod d is exceptional, then you can show that d itself is the sum of a prime and a square. So not for, any just generic n, but if you have some sort of exceptional modulus d, then you can show it's the sum of a prime and a square. So this is, again, work of Friedlander and Ivanets, and it's kind of interesting because the main term that they get is conjecturally incorrect. It's not the main term you would predict from some sort of heuristic application of the circle method or some sort of application of a Möbius pseudo-randomness principle. This main term is incorrect, they get. So that's kind of interesting. It's giving you hints of where the Landau-Siegel zeros are conflicting with what we think is reality, some places where you might go looking if you were trying to show these things don't exist. And then another very famous example is Montgomery's pair correlation function. Okay, so this is something about the spacing of the zeros of the zeta function. And, we know a little bit about this thing, but not very much. And if these Landau-Siegel zeros exist, then this pair correlation function is essentially periodic with period 2. So this is, saying something really bizarre about the zeros of the zeta function, that somehow the zeros are so structured that this pair correlation function becomes, periodic in this weird way. Of course, we don't think this happens. We believe, in the GUE hypothesis that the zeros should behave like, eigenvalues of random matrices, right? And the Siegel zeros are giving us a window into some sort of alternative reality where the zeros of the zeta function would behave quite differently. Okay, so there's some different perspectives on this, and there are many other illusory results that we could discuss. But this is just sort of a flavor, a sampling of some of the very strange, very weird things that happen when Landau-Siegel zeros intrude into number theory. Okay, so let's get a little less wishy-washy and a little more down to details. So what really is going on in all of these results with Landau-Siegel zeros? What is the mechanism driving all of these things? The key point, the main heuristic or the main takeaway is that a small value of L1 chi, and we're thinking again that that's essentially equivalent to a 0 being close to 1. A small value of the L function of 1 forces chi of p to be -1 for a lot of primes p, sort of many more primes than you would just naively expect from, randomness. Here's a very sort of weak heuristic for why this is true. If L1 chi is small, well, then I know I can write L1 chi as some sort of Euler product. And if this Euler product is small, then I'm just looking at the values that chi of p would have to take. It can only basically be 1 or -1. So if I need this to be small, then that tells me that chi of p needs to be -1 for a lot of the primes on the right-hand side. Okay, so that's sort of a very, very basic, naive heuristic. There's a more algebraic way to think about it in terms of class numbers and inertness of primes. Slightly more rigorously, you could prove something like equation 1 here. So I have 1 star chi, that's the Dirichlet convolution of 1 and chi. And this is just an argument on the level of, Dirichlet's hyperbola method, essentially. So you get something here, get some main term sort of thing with L1 chi. You have L prime 1 chi, and there's some sort of error term. And you could take different values of these things and subtract them and get something like equation 2. Okay. So far this maybe isn't terribly enlightening. Just to have the sum of this arithmetic function, 1 star chi, maybe with some logarithmic weighting, and I have an upper bound involving L1 chi. Okay. So I can take the range of summation here to be something depending on d, maybe up to some large power of d. Remember, d is the modulus of chi. Or maybe even d to the a, where a is something slowly going to infinity. Okay, so here's that upper bound again, or here's that equation again, equation 2. And this inequality really is the key. I'll try and explain a little bit of why this is interesting and what sort of consequences flow from it. Okay, well, under the generalized Riemann hypothesis, this actually isn't giving us so much information, because we remember that under GRH, we have a lower bound of 1 over log d for L1 chi. Okay, so the right-hand side of 2 is something going to infinity. But under the assumption of a Landau-Siegel 0, the upper bound on the right side of this equation 2 is actually something going to 0. Okay. Well, 1 star chi, this is a non-negative arithmetic function. So if the right-hand side is something small, then that means that the left-hand side has to, this arithmetic function has to vanish very often. So we might say that it's lacunary. So very often we have the 1 star chi is equal to 0. And you could see what happens when you plug in a prime, and this is 1 plus chi of p. So this is a little more quantitative way to express this earlier heuristic. So this again is saying that chi of p has to be equal to -1 very often. Okay, well, if chi of p is -1, we know another very famous arithmetic function that's equal to -1 on the primes, and that's the Mobius function. Mu of p is also equal to -1. So if I really did have some sort of Dirichlet character where chi of p is equal to -1 a lot of the time, then that maybe says that the Mobius function and this Dirichlet character are kind of behaving like each other. And this is a very powerful piece of information. Okay, so that sort of concludes the historical introduction of things. So in the last part of the talk here, I'll just discuss some of the work that Hung and Alexandru and I have been doing. And this is the influence of Landau-Siegel zeros on the central values of L functions. Okay, so this is the question that we want to ask. We've seen already, we've done this review of some illusory results. We've seen the weird things that can happen if Landau-Siegel zeros exist. And we want to look at the influence on central values of L functions. That might seem slightly weird and unmotivated. I hope to give you a little bit of an idea about why we started looking at this and what sort of interesting things are going on here. So we'll look at 2 specific situations, 2 different families or types of L functions. We'll look at Dirichlet L functions and then automorphic L functions on GL2. Okay, so let's start with the Dirichlet L functions. So just think about the family of L functions LS psi. So psi is just going to range over primitive characters modulo q. So think of q as being some large prime, say, and then looking at all the L functions ls psi, with psi being a character mod q. So it's believed, this is sort of a conjecture going back in one form or another to Chowla, it's believed that the central values of these Dirichlet L functions, L1 half psi, it's believed that these should be non-zero, at least for almost all of the characters. And maybe more ambitiously, you could conjecture that all of the central values are non-zero. So a lot of people have thought about this problem, showing that the central values are non-zero. You have Balasubramanian and Murty. They were able to show that a small positive proportion of these central values were non-zero. So maybe 1% of the characters mod q, say. Ivanits and Sarnak developed a simpler, stronger method, sort of the method that most people use nowadays when they're talking about non-vanishing. And they could show that a third of the characters mod q have L functions with non-vanishing central value. Hung Bui introduced some refinements, a new kind of mollifier, obtained a larger percentage. Just very recently, Rizwan Khan, Georgia Milicevic, and Wo obtained even a larger proportion by using some really impressive sort of algebraic geometry, Kloosterman sum stuff. They got a percentage about 38.5% for a prime q. Okay, so that's sort of the unconditional state of things. And on the generalized Riemann hypothesis, we can show that about half of the central values, L1 half psi, are non-zero. Okay, so again, we think that almost all of them should be non-zero. So the real goal is 100%. And even GRH only gets you about halfway to what you think the truth is. And there's something in here about, you know, the symmetry properties of families of L functions, Katz-Sarnak conjectures, stuff like that. Okay, well, 80% is nice, but even on GRH, you know, it's not super impressive. So you might ask about higher derivatives. You know, this is sort of asking about multiple zeros at the central point. So Bui and Milanovic, they studied sort of the kth derivative at the central point and got some non-vanishing results here. And as this k increases, the proportion goes to 1. Okay, and this kind of makes sense, right? We expect it to be pretty rare for there to be a 0 at the central point. It should be even more rare to have, you know, a 0 of order 10 or 20 or 100 at the central point. Okay, so that's what they're showing here. But we expect sort of 100% for every value of k. And they showed that about 3/4 of the L functions have at most a simple 0. Okay, so none of them should have a 0. But if they do have a 0, then only 3/4, 3/4 could have at most a simple 0. And this is roughly on par with what you get from GRH. Okay, so there's all sorts of different games you could play here, all sorts of different ways you could try and study it. It's all trying to get a handle on the behavior at the central point. Again, this point that encodes something about the arithmetic of the family, its connection with random matrices. Okay, well, what did we show? So there's a lot of notation here. Basically, just think that Q is some large prime, and it depends, Q depends somehow on D, so Q is like some large power of D, D to the 300 or D to the 1000 or something. And if Landau-Siegel zeros exist, then at least half of the central values are non-zero. Okay, so you can see an L1 chi showing up in the error term here. So if that L1 chi is small, you know, smaller than 1 over log Q to some power, then that's a genuine error term. And then you have at least 50% of the central values being non-zero. Okay. So if Landau-Siegel zeros exist, this gives you some sort of match to the GRH result. And it's possible that by working harder and doing some things that we didn't try to do, you might actually be able to beat GRH. You might be able to go beyond GRH a little bit. there's various ways that you could refine this, try and modify things. The important thing to note, though, is that Q really does have to be like some fixed power of D, right? So if Q is much, much larger, then the distorting influence of the Landau-Siegel zero disappears, just like with primes and arithmetic progressions, right? If X is much, much larger than D, then the primes up to X, they actually are equidistributed, you know, among the different residue classes. So there's something similar going on here. We have another theorem about what happens with multiple zeros, and we show basically that 100% of the L functions can have at most a simple zero. Okay, so you know, even on GRH, you're only getting something like 3/4, and here you're going beyond GRH. If things do have zeros at the central point, for basically everybody, it could only be a simple zero. Okay, so we're getting some strong results here. Some interesting things here with Dirichlet L functions. Okay, so that wraps up what I want to say for the moment about Dirichlet L functions. Let's talk a little bit about automorphic L functions. So these would be L functions LFS of modular forms on S2Q. Okay, so these are new forms of weight 2 and say prime level Q. We could look at different weights other than 2. We'll just stick with 2 for simplicity. So again, think of Q as being some large prime here. So modular forms, weight 2, level Q. Okay, by Eichler Shimura, some other people, we know that you could look at an L function of the Jacobian of this sort of modular curve of level Q, and the L function of the Jacobian of this variety is given by a product of these LFSs. Okay, so the L function of the Jacobian is the product of the L functions of these modular forms. And then you can start talking about things like the Birch and Swinnerton-Dyer conjecture, or more properly, generalizations of that conjecture to sort of higher order algebraic things. So somehow the order of vanishing of these modular form L functions should be telling you something about the algebraic rank of the Jacobian. Okay, so this is just a souped up version of the usual Birch and Swinnerton-Dyer conjecture. So we're really interested in the order of vanishing at the central point. So maybe let R sub F be the analytic rank of F, i.e. the order of vanishing of its L function at the central point. Okay, so if it doesn't have a 0 at the central point, the analytic rank would be 0. If it has a simple 0, the analytic rank would be 1, and so on. So this is what we're interested in. How much can these L functions vanish at the central point? Well, we do have some tools, some heuristics to sort of help us out here. All of these L functions are self-dual. So the root number in the functional equation is either +1 or it's -1. And accordingly, we say that a form is even or it's odd depending on the root number, okay, according to whether it's plus or -1. And fortunately, this is a good piece of terminology because about half of the forms are even and about half of them are odd. It wouldn't be a very good definition if 90% of them were even and 10% of them were odd. Okay, so we're in a 50-50 sort of situation here. And this is a little bit of an abusive language, but the parity of F is the same as the parity of RF. Okay, so that parity isn't quite the same there. But the order, the parity of F, that tells you the parity of the order of vanishing at the central point, and you see this from the functional equation. Okay, so what do we expect here? Just like with Dirichlet L functions, we had some sort of conjecture about what should be going on at the central point. What do we expect to be going on here? Well, there's some very nice conjectures. Conjecture of Brummer and Murty made around the same time, but independently of each other. They conjectured that almost all of the even forms do not vanish at the central point or have analytic rank equal to 0. and they conjecture that almost all of the odd forms have analytic rank equal to 1. Okay, so note that just from the functional equation, an odd form has to vanish at the central point. And their conjecture is somehow like a minimality statement. It has to vanish, but it should only sort of vanish once. It should have a simple 0. Okay, so this is their conjecture. If you're even, you basically all the time shouldn't vanish, and if you're odd, you should only vanish to order 1, as little vanishing as possible. Or to put it in other terms, we expect that 50% of the forms should have analytic rank 0, 50% have analytic rank 1, and 0% to have analytic rank 2 or more. Okay, and so this is a very nice conjecture, very clean, exactly what a conjecture should be. And Ivanits and Sarnak have some very nice work showing essentially, not quite, but essentially, that this conjecture implies that there are no Landau-Siegel zeros. So if you do have this very nice 50-50 zero situation, 50%, 50%, 0%, then this implies there actually are no Landau-Siegel zeros. And the reason that we got interested in these central values was this work of Ivanits and Sarnak, and we were interested in some sort of like converse direction, like what happens if there are Siegel zeros, like does anything weird or interesting happen at this central point? So I won't say anything more about this work of Ivanits and Sarnak, but that really was our starting point for our investigations. Okay, well, if you take this conjecture of Brummer and Murty and you do, some Burchens, Winard, and Dyer to it, this gives you what you expect, the rank of the Jacobian to be. You would expect that the rank of the Jacobian would be about half of its dimension. Okay, so every time there's a 0 from one of those L functions, that should give you some contribution to the dimension, and there should be about half of them having zeros according to the conjecture. So we should get about half of the dimension being the rank. Okay. So what do we know towards this? You have work of Ivanits, Luo, and Sarnak. So using GRH and of course some Burchens, Winard, and Dyer stuff, instead of getting 1/2, they can get an upper bound of 1 plus epsilon. Okay. So you would want 1/2. They can get 1 plus epsilon. Kowalski, Michel, and Vanderkam, they could remove the GRH condition and got a constant that was only slightly larger, this 1.8 or 1.1891, so just a little bit larger than 1. These upper bounds, I'm saying BSD. This is only to say that the algebraic rank is equal to the analytic rank. If you don't say anything about BSD, then this is giving you something about the analytic rank of these L functions. Okay, so that's sort of what we know. And here's what happens if you have Landau-Siegel zeros. Okay, so this is the way we can phrase it. So either, this is condition 1 here, either there are no Landau-Siegel zeros. Okay, so you have some sort of nice lower bound for L1 chi. Or if these things do exist, then you essentially get this conjecture of Brummer and Murty. Okay, well, sometimes. So you can read it here. I don't want to read all these words at you if you don't want to read them. But there is some sort of condition on chi of Q. Okay, remember Q is the level and chi is the weird Dirichlet character that has a Siegel zero attached to it. So if chi of Q is equal to 1, then we get that the rank of the Jacobian is basically 1/2 the dimension, just like the conjecture says. And if chi of Q is -1, then we get the lower bound and the upper bound is off by a factor of 2. Okay, we get a 1 instead of a 1/2.
Guy, sorry,
Yeah.
can I say something?
Yep.
So I think for the second statement, this is unconditional. It's not under BSD.
Okay, so yeah, so there's some BSD, maybe not BSD, but yeah, thanks, Hung. Yeah. Okay, so this is what we have here, assuming Landau-Siegel zeros exist. You get the conjecture, of Brumer and Murty, this really nice conjecture about the rank of the Jacobian, or you almost get it up to a factor of 2. Okay, so another way to think about this is in terms of the central values of these L functions. So another way to think about this is assuming the Landau-Siegel zeros exist, we show that 100% of the forms have analytic rank at most 1. This is when chi of q is equal to 1. Or in the other case, where chi of q is minus 1, 100% of the forms have analytic rank at most 2. Okay, so in general, we don't know anything like this. All we can show right now, we can't rule out at present the possibility that a very small but positive proportion of forms have a very large order of vanishing. You know, so we don't think this is true, but there could be like 1% of the forms have an order of vanishing that's like 200 or 300 or something ridiculous. Okay, but we show if there are Landau-Siegel zeros, this actually doesn't happen. And this weird condition on chi of q, I don't want to say too much more about it, but it basically arises from root number considerations. You have the root number of your modular form L function, and when you twist by a character, the root number of the twist is somehow controlled by the Dirichlet character at q. Okay, so you have to keep track of this root number somehow, but I won't say anything more about that. All right, so in the small amount of time remaining, I just want to say something briefly and very broadly about how these proofs go. The proofs are sort of similar. Obviously, when we work with GL2, it gets much more complicated. So I'll just focus on the Dirichlet L functions. So how do you go about trying to prove something like this? Okay, well, first we start where everybody starts when they think about non-vanishing of L functions. We use the mollifier method. Okay, so I have this inequality here. This is just Cauchy-Schwarz, this equation 3. I have some complex numbers, b psi. You just do Cauchy-Schwarz. That's just all this is. Okay, well, this is nice, but what am I supposed to do with this? Well, if you apply this directly, if you just apply Cauchy-Schwarz directly with these b psi's equal to the central values themselves, then you actually don't get a positive proportion, because you have a first moment and you have a second moment, but they don't have the same size, right? And we know that Cauchy-Schwarz is only sort of sharp when everything is, you know, nice and like a linear, you know, everything is like constant size basically. Okay, well, things are not of constant size. There's some weird fluctuations. So you need to deal with that somehow. And we want to additionally take advantage of this lacunarity property. We want to somehow get Landau-Siegel zeros mixing around in here. So we actually are going to study the non-vanishing of a product, the L1/2 psi that we're kind of interested in. And then this, you could think about it as being an auxiliary L function, this twist by chi. And if you look at the coefficients of the Dirichlet series, you see that this 1 star chi shows up. We remember from our earlier discussion that 1 star chi is lacunary, at least when these Landau-Siegel zeros exist. So this Dirichlet series, it should have a lot of coefficients that are 0, and somehow that is going to be very useful for us. Okay, so you don't apply this Cauchy-Schwarz argument with just the central values themselves, but you also throw in something called a mollifier. This is a short Dirichlet polynomial designed to dampen the large values. Here it is sort of explicitly if you care about what the definition is, and you can figure out very easily what the coefficients are. There's something involving the Mobius function, something involving 1 star chi. That's very important. And you choose this basically heuristically from looking at the Dirichlet series coefficients of the inverse, and you just sort of guess that this should still be a reasonable inverse even if you're at the central point. There's sort of no good reason it should be, but it turns out that it is. And Q is a large power of D, so this mollifier is actually quite short compared to, say, the lengths of the the sums coming from the approximate functional equation. So this is something that's quite different from the usual non-vanishing games where you want this mollifier to be as long as possible. Well, here in this sort of illusory or alternative setting, you only need a very short mollifier. Okay, so this Cauchy-Schwarz thing reduces the problem to studying first and second mollified moments. Well, it's the first moment of like a product of two L values, and it's the second moment of a product of two L values. So it's really better to think about it as like a second moment and a fourth moment, or a twisted second moment and a twisted fourth moment, because we also have to think about a mollifier. Okay, so this is sort of right at the boundary of what we know how to do. The fourth moment with a little Dirichlet polynomial thrown in. Basically, any family of L functions we can think of, we only know how to do the fourth moment, or we can do at most the fourth moment plus a little bit more. Okay, so just heuristically, what's going on here? What would we expect to maybe work? So you have this approximate functional equation. You can write the central value as two sums of length the square root of q. There's something involving a root number. There's some character values, whatever. Okay, well, clearly chi of 1 is just 1. There's no like cancellation or oscillation that's going on there. So maybe you would think, okay, well, I'll pull out chi of 1. That's kind of, nothing's going on there. But maybe when n is larger than 1, maybe these character values cancel out on the average. So you might expect that maybe on the average, you get something like this approximation here. Maybe the central value is like 1 plus a root number. Okay, something like this. This heuristic is completely false, so please don't try and prove any theorems based on this heuristic. Okay, so maybe this is true. This root number also experiences cancellation. So if you look at this first moment, that gives you, the L function is like a constant in the first moment sort of L1 sense. And you can say something similar for the second moment. You maybe hope that these oscillatory values cancel out on the average. And if this was all true and you run through the Cauchy-Schwarz, this would give you that 50% of the central values are non-zero. Okay, so that exactly matches with GRH, with what we're getting from Landau-Siegel zeros. Okay, so this heuristic doesn't really work. It kind of works for the first moment. It doesn't really work for the second moment, even when you mollify. But in a sense that I won't get into here, this heuristic basically does work when there are Landau-Siegel zeros, and you can essentially get perfect mollification. So the oscillatory terms sort of wash out in the average, and the non-oscillatory n equals 1 terms are really all that contribute to the percentage of non-vanishing. Okay, so from this point of view, the 50% is some sort of very natural barrier in the problem. And that gives you a sense of maybe why the Riemann hypothesis only gets you 50%, because the Riemann hypothesis is about, very natural things. It doesn't deal with the natural. Okay, so some technical points, maybe some red meat for some of the experts. Okay, so the second moment is the hard thing, which is we recall is more like a fourth moment. You have some approximate functional equation stuff, use some character orthogonality. You're staring at something like this equation, have a sum over 4 variables here. And the diagonal is always very easy. And then, of course, you have an off diagonal that you're trying to control. You're trying to show, in this case, that it contributes only to the error term. Okay. Now, why would that be the case? You basically, okay, I'm going to skip this. That's something about a main term. That's boring. Skip more of this. Okay, so the off diagonal, you want to show that this contributes only to the error term. And again, I'll give another heuristic for why this is true, just in like the 2 minutes I have left. So this is some sort of shifted convolution problem for 1 star chi. You can think about 1 star chi as sort of being like a divisor function. It kind of is like the coefficient of an automorphic form on GL2. So this is some sort of shifted convolution problem like this, and you have this non-zero shift h. But we expect that the multiplicative structure of n and n plus h, we expect that these are basically independent, right? We don't think that addition and multiplication should really see each other. So somehow the lacunarity of 1 star chi should strike twice. And this would give you something like L1 chi squared in the main term of the off diagonal. And if we're thinking that L1 chi is small, then certainly when you square it, it's really small. Okay. So that's a little bit of a heuristic about why this this is small maybe, and why only the main terms come from the diagonal gives you the only main terms. Because you have to do some shifted convolution stuff, and it's very tricky to see, you know, what's going on here. Okay, so this fourth moment, you have to do some interesting Kloosterman sum stuff, and it turns out that we don't need any super crazy spectral theory. You can just basically get away with the Weybound. So that's kind of a nice, interesting thing that happens here. In these sums, you get some very nice exponential sums that come out, and you can treat them in a very nice fashion without having to go for the full power of spectral theory. Okay, I think I'll stop here. Thank you very much.
Thank you. Okay, all right. Okay, so some late applauses. That's great. Okay, thank you, Kyle. Very nice talk. And I'll open up for questions now. Okay, if not, I can ask a question myself. So can you go back to the last slide?
This slide?
Sorry, the one before. So yeah, I want to ask something about that. So in this case, like chi is a character of very small modules, right? I mean, compared to the size.
Yep, right.
Okay. So you think of it more or less like a constant one.
Right. Yeah. It's basically like a constant. So 1 star chi. You sort of think about it just like the regular divisor function.
Mm-hmm. Yeah. And so the thing you said about, I mean, it said like heuristically about the lacunarity striking. How can you see this from the in the actual proof? I mean, so what you do is similar to what other people do to treat this.
Right. So yeah. So how it comes up in the actual proof is so you have n and you have n plus h, and you somehow like want to separate these from each other. So you need to use some sort of like delta method or Kloosterman circle method.
Kloosterman sum at some point.
Yeah, something like this. And so you do some sort of delta method to separate the variables. You do a Voronoi summation, and the main term of this Voronoi summation has an L1 chi coming from it. And you did 2 Voronois, one for each sum, so you get 2 L1 chi's. And then you have to show that the error terms are smaller.
Okay, but the treatment of the error terms, in that you don't use that these comes from receptional chi, right?
Yeah, that doesn't really come into the error term analysis.
Okay,
but
interesting.
But it plays a big role in the main term analysis.
The main term. Which is the less complicated part? Is it fair to say? Or?
Yeah, I skipped over it. The main term analysis is complicated in a different way, just trying to go through the mollification and show what things, show that things simplified to something really nice. It can be a little bit hairy, but it's
I see.
Maybe not as technically demanding.
Okay. All right. Looks nice. Very cool.
Hi, Carl. I've got a quick question.
Hi, James. Hey.
So do you need moderately strong Siegel zeros for this application where L1 chi is of size 1 over log d to some fairly large power? Sometimes these Siegel zero effects happen as soon as L1 chi is little o of 1 over log d. Do you believe that like a similar effect should be happening in that situation as well, and it's just for sort of technical reasons that you want to have more savings so you can treat some things trivially, or is there sort of genuine issue if L1 chi isn't quite such a strong equal zero?
Right, good question. So yeah, we definitely believe that as soon as L1 chi is just little o of 1 over log d, this should all work. Yeah, it just turns out that if you really want to be that precise, then it's like pretty technical and you have to be really careful with a lot of things, and it's kind of annoying. So to just try and illustrate the main ideas, we let ourselves use a little bit stronger Siegel zero. But you should be able to do exactly what you're talking about.
Yeah, okay, thanks. And one other potentially like slightly dumb question was just in the statement of your main result for GL2, where you have this one bound for when chi of q is 1 and one bound for when chi of q is -1. Isn't q restricted to being a prime, and so 100% of q's have chi of q being -1?
Yes, I didn't mention that, but I should have. Yeah, so when chi of q is equal to 1, this is just a very sort of thin sequence of the primes, and almost always it's going to be the -1 case.
But this still works. Okay, yeah, fine. Thanks.
So you have the stronger result for the one that appears the least, right?
Yeah, that's right.
Okay. Bummer.
Yeah, and this this point that James brings up, it's very closely related to this Ivanets-Sarnak result I mentioned about if the Brumer-Murdy conjecture is true, then there are no Landau-Siegel zeros. It turns out that the root numbers and this kind of thing, it plays into what they're doing, and yeah, you definitely want it to kind of go the other way, and there's very good reasons why it doesn't go the other way.
Right.
Sorry, can I ask?
Sure.
Hi, Carl. Thank you very much for the
Hello.
talk. I have a very basic question. Could you please explain again why your second moment is more like a fourth moment, which it definitely looks like one?
Sorry, your question is why does the second moment really look like a fourth moment?
Yeah, like at what point exactly does that happen?
Sure. So let's see what I want to look at here. Right, so we want to somehow use the lacunarity induced by Landau-Siegel zero. And to do that, we need to look at a product of central values, not just L1 half psi, which is the thing that we actually sort of care about the most. But we introduce this auxiliary central value, L1 half chi psi. So we're twisting by chi. And then when we take this product, we get this nice 1 star chi, which we need. We need that key piece. But now that means that we have to deal with a product of these central values. Okay, so we have to look at a first moment of this product, and then we have to look at a second moment of this product. So a second moment of this product is like 4 L values. So that's where you're getting like a fourth moment coming from.
Yeah, so you're looking like at a shifted product of a bunch of. So if you translate that into the Riemann zeta land, then you basically look at a product of 4 zetas and you just induce a shift.
Yes, yeah, that's right.
So you're doing like Murray-Hash's integral for L functions.
Yeah, I guess so. Yeah, that's one way you could look at it, I suppose.
Okay, that's very interesting. Thank you very much.
I guess you're still open for questions. I mean, if the speaker is not tired.
Ask away. No one has a
Sorry?
question?
Okay. Maybe not. Okay, then let's thank Kyle again. Whoever have his mic off.